vAXI. 5 easy steps to build your system on chip. During this tutorial, we will show how to set up system on chip on FPGA, including synthesis and simulation environment, and we will do this using vAXI IP module. The vAXI IP module and its software allows easy connection of user modules to AXI and Avalon bus and subsequently to ARM system, including easy setup and auto-generation of synthesis and simulation environment. We will generate today automatically a functional synthesis environment which looks like this one, including ARM inside, connected to the vAXI module, which behaves like a switch towards user modules and having multiple variable interfaces like memory and register interfaces. In addition, the user could talk to his logic through JTAG connection connected to Altera system console running on a PC. In addition to this automatically generated synthesis environment, the software will generate automatically a simulation environment, completely functional one, allowing sending commands and emulating ARM using special command generator and AXI master simulative model to their user logic connected to vAXI. The design flow of vAXI is very simple and consists of 5 easy steps. During the first step, we will customize and generate vAXI module. On the next step, we will employ the automatically generated synthesis environment to perform synthesis and place and route of the device. Then we will program the target device, real board, and we immediately could start talking to our custom logic, our memories and register box through system console. Once everything is set, at the step 5 we can continue and add to our project new user modules that could be connected also to vAXI module. So let's do this. Let's take 5 minutes to do the entire process. We trigger vAXI software to configure and customize vAXI module. Here we can define different clocks, frequencies for the clocks. Here we define we can define the target device. Here we can define the AXI protocol, XI4 or XI Lite. We can choose different widths. It is completely configurable. And on the next step, we define the interface to the user logic. We can define any number of ports. We'll choose one for the sake of this simple example. We create the port name. This will be the prefix in the RTL to all the interfaces of this port. We choose the clock for this port. We can choose different buffer interfaces, including different protocols, protocol flex, and so on, and also widths. In this example, I will generate RAM interface and register bank interface. RAM interface will reside in these addresses. As you can see, the width is completely configurable as well as the depth. Similar for the register bank. I can choose the register bank to be either internal or external. I can choose double buffer option for the register bank. I can create also simple bus interface for off-chip interconnect and so on. Here's the summary, and here I'm giving the name, my first vAXI, and choosing a directory folder to save entire files and trigger QSys. QSys is automatically triggered and configured, and all the synthesis and simulation environment are generated automatically. We can see them here in this folder. We can see here the test bench files, we can see here the top file of vAXI with my port prefix. We can see here simulation environment, synthesis environment, scripts for testing, and in a second, when QSys finishes, we will see also the files of QSys automatically generated. Here we see them. Okay, so now once we generated all the files, let's open Quartus using automatically generated synthesis environment. And let's take a look at the QSys environment that was automatically generated. Takes a few seconds. Okay, we can see here special ports for external XI connections. We can see them employed here. We can see the JATA connection to system console, and we can see here the LED connections. Now we just run the synthesis. Once synthesis is over, we will program our device as follows. And now we can move to step 4 and talk to our device. Let's trigger system console. Just to remind you, during the files generation, scripts were generated. Here's a sample script which talks to the memory and to the register bank and then plays with the LEDs. So let's trigger it. Execute script. Now we can see real-time run with writing to the memory, writing to the register, and playing. And the time is up. And congratulations! Your system on chip is fully functional on the real board, and you can now continue with your project and add additional functional block to a working synthesis and simulation environment.